from the studies and listen. Okay, so like yesterday we are going through this the power flow control capability of UPFC. So we'll try to see this. So in this case, so yesterday we have stopped here. So this is the case. Like so the power transfer is so the UPFC can be used to control the power for both positive as well as negative region. So and it can control both reactive as well as active power. So this is the case here. So this line indicates the uncompensated one. So normal before compensation. Now when you are giving this factor as VPQ V by X. So actually what you have V square by X. You have. So here VPQ is nothing but the injected voltage. So injected series voltage. Okay. So when you are making it at 0.5, then the power transfer capability will increase. So the power transfer capability of the UPFC is independent of the del. See here. So even at del is equal to 0, it is able to transfer the power. So 0.5 here it is. So here minus 0.5 it is there. So it is there. So you can either increase or decrease the power transfer capability. Similarly, it can be for the reactive power here without compensation, with compensation, positive, with compensation, negative direction. Okay, so this is what you have. Then another one you can see is the phasor diagram, which this defines relationship between Vs, Vr, and Vx, the voltage phasor across X. So this one, so when you, if you just summarized one, you can see. So this one, the figure we already have, the figure above. So here now the relationship of this Vs sending in voltage, Vr receiving an voltage, and Vx is nothing but the voltage across this line impedance X is shown in this, and is calculable within 0 to VPQ max and angle to 360. So it can be 360. So now here what you are seeing is, you can see this in this case what you are having is Vs. So here Vs, when you add this VPQ, then you are getting is V cell effective, V series effective you are getting. So okay, so effective voltage is this. So this is your effective voltage. Okay, so this. And then now VR is nothing but Vs or VSEE minus Vx will give you VR. So this is there. So irrespective. So now here delta will also change in this case. Okay, so this is what you have. So Vs and VR. Previously without this it will be this much only it will be. Now when you are adding or injecting a voltage VPQ, this voltage, then your resultant effective voltage will become this. Therefore the delta will also change. So this is what you have, the voltage phasor diagram given here. Just as explained before, you can see is the inserted voltage phasor VPQ is added to fixed sending end voltage phasor Vs to produce this. So this one. Okay, so this is then the difference of effective sending end voltage and the receiving end voltage actually provides the compensated voltage phasor Vx across this. So the difference of Vs or this minus this will give you Vx, which is actually the compensated voltage across the uh, inductance X inductor. Then now another point is, as this angle is varied, this rho is varied over its full cycle range, so it will be actually moving like a circle, so operating, so it will operate within this. So this is where it is operating. So Vs given tip as a center here, then when you operate, so radius as this radius as VPQ, so it will operate within this circle. Okay, so later on the significance of this circle will come later on when you do that contouring of that different power control. So the area within this circle, so area within this circle, okay, so this circle obtained with this defines the operating range of V phasor, whereby it is the actually which can be achievable of compensation of line. So you will be able to achieve this compensation along this area. Okay. Then another one is, you can see just the rotation of phasor VPQ with angle rho PQ modulates both magnitude and angle of phasor Vx, and therefore both transmitted real power P and reactive power Q are vary with rho PQ. So this, and in a sinusoidal wave. So this is the variation of this with P when VPQ is 0. Then this is at, see, this is your QR again in the sinusoidal manner, and this is the overall PQN overall of this. Okay, so this is what actually it means. Then next topic you can see is independent real and reactive power flow control. So UPFC can also control the reactive and real power independently without depending on one another, whereas in STATCOM and SSC it was not possible, right? So they have to depend for one another. One parameter has to be there in order to control reactive and active power. So now here, in order to investigate the capability of UPFC real and reactive power flow in the transmission line, so let us read for this. Okay, so now case one, you can assume this first case. Okay, so this is shortener, you can have this case, we will have two cases here. Case 1 is equal to V PQ is equal to 0. Means here what happens? Means this is your, what is this? Uncompensated, no? Uncompensated line. So then what will be your power? Power will be given by, so here, then in this case, what will happen is, this is the case. Therefore, the normalized power PO will become this, and then QO will become this. Okay, so PO. So this is your case one, uncompensated and compensated in the version. Then plus another thing will be there. So normal one. So what we will have is, so it is becoming like this. So in this case, what you are having here, this is the case. You don't have this, so you have only this one. Okay, so you don't have this. So this is your X, and then this is your VS tail, and then this is your VR angle 0. Then what will be your power here? So power, actually normal power is given by VS VR by X sine tail. So this is what it is there. So here it is given, which is equivalent to this, and then Q is given by V by VS VR by X 1 minus cos tail. So this is the thing. So at case one, without compensation. So this is without compensation. Okay, so without compensation you have that. Then now if you draw the line, if you plot this one, what will happen? So can you plot? So here now you are plotting. So you will have this, you have to plot this. So please, can you draw this table? Hello. Okay. Okay, so can you draw now? You have here is del PO del, and here you have is, you can have minus Q O R del. So can you find which is equal to here? PO del is equal to sine del. You are, so we are considering this normalization factor, this one as, we are right now while plotting, you can consider this one as 1, normalized factor 1 del, and then QR, this one is equal to, you can have is 1 minus cos del. Okay, so now can you have, when del is equal to 0, del is equal to 30, del is equal to 60, del is equal to 90, then 120, 150, 180. So how much you are getting when del is equal to 0? PO how much? What is PO?
0.
Hello.
0, sir.
0.
PO
0,
0.
sir.
PO. This is 0. QO
0, negative 0.
0, sir.
1 minus cos 0 is 0. So 0.
0.
When 30,
0.5.
0.5. Here 1 minus cos 30.
0.134, sir.
So minus 0.134. No, so you have minus 0.134. Then sine 60.
0.866.
0.866. Here 1 minus cos 60
Minus 0.5, sir.
minus 0.5. Then here 90.
1, sir.
Sine 90 is 1.
1.
Here it is
1.
1, sir.
1 minus cos 90. 1, 1. So here it is, sorry, 1. We have 1. Then is sine 120.
0.134, sir.
Sin 120 remember sir?
0.866.
0.866 remember na? 66. Then here 1 minus cos 120
Minus
1.5. 1.5 or 1.5 no?
Yes, sir.
Then let's sin 150. Sin 150 how much? 0.5.
2.5.
And here 1 minus cos.
1.866.
So minus 1.866. Then here it will be 0. Here it is 0. 1 minus cos 180.
2, sir.
2 mm.
2, sir.
Yes, sir.
Okay. So this table you can have this. So now when you plot, so can you plot now? In same, so here you have del, then you will have P and then PQ. So can you plot this? So when you plot this, what you are getting? So you plot it. So when you plot, you will get this. So this is for PO del. So you are getting no, and this is for QO del. Getting?
Yes, sir.
So here now
Yes,
you
sir.
see here it is like this. So at pi it is maximum. So that is why it is here. And power will start in this case it is this one real power. But maximum power in maximum real power is 1. But in case of reactive power, maximum you are getting was 2, no minus 2. So this is where it is starting. So this
It
is your
180.
so control limit. So this is your locus of this where it is. So here real power will be 1 at del is equal to pi by 2 and real power will be minus 2 at del is equal to pi. So here this is your center locus and minus 1 pq minus 1 1. So you have no in table. If you go back to table you will have see that del q when po is 1 del q was minus 1 somewhere else. So at del is equal to pi by 2. So this is what you have seen. So this is what you will see. So controllable you can see that this is without compensation. Okay, so normalized one without compensation. So minus it can be QR be watching. Then if it is plus, then this graph will go up. No, so plus QOR. Is it like that? This is plus, this is minus. Just a mirror image. Is it okay? So how to plot this one? Is it okay? So
Yes,
with
sir.
increase,
Yes, sir.
increase slowly, then it will go and then it will again reduce the powerful. So now the relationship between this is the case V by is as this. So you will have is QOR is equal to. So which is actually this is a equation of circle. Equation of circle. So this you have is you can have this equation of circle. Okay, so circle. So now this equation 3.41 actually describes a circle with radius of 1 around the center defined by the coordinate p is equal to 0 and q is equal to minus 1 in PQ plane as illustrated for positive values p in figure this. So this positive values of p is this and then negative values of q. So this is what you have. Circle. So this now if you go back then it will come 360 by watching then it will come like this. Okay, 36. Now if you are taking the q value positive then it will come like this for positive q value. For negative p value this is then 360 पे watching 360 पे watching table will be like this. Okay, so this is positive Q, and for this you have is negative Q O R. Okay, so this is what it is. So control range, later on we will come to that control range here. So this now another point you can write down is each point of this circle gives the corresponding PO and QOR values of the uncompensated system. So this is what actually uncompensated system at a specific time. So for example, at del is equal to PO is 0, that is what we have seen. So at del is equal to 90, so both maximum, but one is at negative and another one is at positive. So this is equal to the, so this one, this first case, this is the case. Okay, so this circle gives when del is equal to 0, PO is 0, QO is also 0. When del is 30, PO is 0.5, whereas QO is 1.34 minus 0.134. So this is slowly it is coming and then it will increase. This is what actually means that. Now next point you can write down is case 2. This is second case. Okay, case 2. First case, what was the case 1? First case, what we had?
Uncompensated.
So uncompensated here, that injected voltage VPQ
Is equal to 0.
was 0, no, in that first case. Now case 2 compensated, so you can have VQ is not equal to 0.
0.
So then VPQ is not equal to 0. So here VPQ is not equal to 0. So your case 2, the VPQ is not equal to 0 this case. So case 2. So that means compensation. Now you are compensating. Okay, so here you can write down compensating. So you are compensating the line. Compensating. Okay, so you are injecting some voltage to the system, compensating. Then in this case, what happens? The real and reactive power change from their uncompensated value PO. This is uncompensated value, real power uncompensated, reactive power uncompensated, as a function of magnitude VPQ. This is injected voltage and the injected voltage angle of the injected voltage phasor VPQ. Okay, so that is there. Then since another point, you get this rho is an unrestricted variable where from it can vary from 0 to 2 pi, means 360 circle na. So it is the boundary of the attainable control region for P at del and rho and Q at del and rho. Equation 3.34 and 3.5 is obtained from complete rotation of phasor recurve. So complete rotation means you can have this circle. You have no this like that Vs within. Then with VPQ as radius, you can have this. So complete maximum. So from the power equation, so from that equation to power equations, this circle is defined by with the radius of this. The boundary circle can be described by following equation. So you can have. So first one, this is real power compensated, uncompensated, reactive power compensated, reactive power uncompensated. Will give you this. This is your radius. So equation of circle again. So from that circle equation you can. So the circular control region defined by 3 port are shown in. So now can you draw for this one? So this you can just see. Now can you understand this part? Hello? when del is equal to 0 here, in this case, so you can put the value of del is, or in that equation 3.34, you can put the value del is equal to 0, and then you will find in the above case when del was 0, p will be, what will be p? When del is 0, p is, hello, when del is equal to 0, p is equal to 0 and q is also 0. So radius is here. Okay. Now when p is equal to 30, when del is 30 degree, when del is 30, what is your p? P, any idea what was p? P is 0.5, no?
Yes.
Then q
Negative.
is equal to minus 0.134. So now when you plot it, so 0.5 here and then your 1.13. So with this as center, you draw circle. So this is your controllable region. Then similarly, when del is 60, del is equal to 60. What you have? When del is 60, p is equal to how much? 0.866. And q is equal to
0.5.
q, what you had?
0.5.
1 minus cos 60.
0.5.
So 0.5, no, minus point. So when you plot this, so here you will have 0.86 and the p only this 0.86 somewhere else, and then minus 5 you can take this. So with this as center, you draw this. So for any region you will be able to draw. Then similarly, when del is equal to 90, del is equal to 90, p here is how much? Sin 90 is p is
1.
1, q
Minus 1.
minus 1. So now you bring that to, so you plot here, so 1 here and then minus 1 here. With this as center, you draw a circle here. So this is what you'll have. So VPQ as max. So VPQ max as a, so right now while you are while drawing this one, we have considered this radius as 0.5. Okay, so VPQ as 0.5 and x as 1 per unit. So then we are getting this. Then you can have different events. So VPQ max, by defining this, you can have that. So you can try this one in your MATLAB programming data or that Simulink database. So then you will be. So just put that value of data del there. So this is how it is happening. Now if you go for when del is equal to 120, can you draw? Hello, can you draw when del is equal to 120? When del is equal to 120, can you draw? Del is equal to 120. So what is your P?
0.86.
Sin 120 is 0.866. Q 1 minus cos 120
Minus 1.5.
minus 1.5. Now can you shift it? So you can have is 0.866 somewhere else here, then 1.5. So here now if you draw this is 0.86 is cut to somewhere else here, no, this 0.866, if you can have this.
Yes.
And then 0.1.85 where it would be, 1.5 where it would be, can we take this one here? So with this as circle center, you can draw this. So it will be somewhere else here. 150 be watching. 150 when del is 150
Is equal to 0.5.
Sin 150 0.5
0.5.
and then 1
minus 1.866.
So minus 0.866. So somewhere else here, where it will come. First one is 1.5, no?
Yes, no.
Yes, sir.
150.
5.
0.5. So Anna in there,
0.5.
that, so it is coming here, and minus 0.866 is, so somewhere else here. So this is center, and then radius is 0.5. You draw this. 200, 180, 180. Can you draw now? Where is 180? 180. Sine 180 is 0. Sine 180 is 0 here. Then
-2.
Minus
minus 2.
somewhere else here. So with this as center, draw now. So here it will be somewhere else here. Okay, 180. Delay 210 and the other. So it is coming slowly. It will come and then it will reach here. Okay, so 360 whole circle. Is it okay? This is how you are able to actually do the compensation. You are able to control active as well as reactive power flow independently. You are able to control it. So the control structure. So this control structure we'll do in next class. Kille wa gachpiga ni kille wangchu. Any idea? Gachpiga kokhatse
network problem ye du me sa theta kabra ko ni messenger na jun lo lab da network problem o me lab de sa.
Oh, okay. So if you have any, please feel free. So you can try this one, okay? Dachigani. Now we have done till 190 and 90 degrees. So you can go for 120. Where you will go 120, then 150, then
180.
180.
180.
210, then 210. Means
270, 360.
270 delay and 360. One cycle, the whole cycle you try to do it, okay? By keeping
Okay,
that
sir.
radius as 0.5, you keep radius as 0.5. VPQ max as 0.5. Okay.
Okay sir.
Okay, sir. We'll try.
Okay. Time ever you do it. Okay, so then you can try. Okay.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
sir.
Okay.
Thank you sir.